In this video, we will be going over section 7.3. The title of the section 7.3 is adding up sequences to get series. Okay, basically, in this section, we will formally be defining a series, and we'll be going over various types of series and some arithmetics that we can do with series. Okay, I want to start with this definition. Definition of a series of real numbers. Okay, here is how we define a series of real numbers. A series, which is denoted by sigma k goes from 1 to infinity ak, is the sum of the terms of a sequence ak of real numbers. Okay, so in other words, this series, sigma k goes from 1 to infinity ak, is nothing but the summation of all the terms in this sequence. A1 plus A2 plus A3 plus ak plus . That means you take the summation of all the terms of this sequence. Okay, and in this series, for each positive integer k, ak is called the kth term of the series. For example, in this series, if you look at this series, this is the kth term of this series. Okay, similarly, this is the third term of your series. This is the second term of your series, so on and so forth. Okay. All right, let's move on. Next, I want to walk you through this example. Rewrite the series. This is the given series. Sigma k goes from 5 to infinity, k over k squared plus 3, with the index starting at 0. Here, in the given series, the indexing starts at 5, right? So, but in the new series, but we need to have the same series, but with a different starting index, which is 0. We need to start our series with 0. So what we do is we follow a similar procedure that we did in section 7.1 when we were dealing with sequences. We wanted to write sequences so that the starting index is 1, right? We follow a similar process here. So what we do is I'm going to write the new series starting at the index 0. I'll use new indexing variable to be n. I want my new indexing to start at 0, 0 to infinity. Now I need to figure out what I'm supposed to put here. Okay, here is what you do. Just like what we did in the section 7.1, we start with this equation, k is equal to 5. This is the indexing equation, starting index in the original series. So I start with that, k is equal to 5. Now, notice that my starting index of the new series should be 0, right? So I'm going to get a 0 in my right-hand side in this equation. For that, I'm going to move this 5 to the left-hand side. That will give you k minus 5 is equal to 0. As we needed, we have 0 in the right-hand side because our starting index should be 0. Now I'm going to introduce my new variable. I'm going to call my new variable n. I'm going to take my left-hand side to be n. Okay, so that means n is equal to k minus 5. This will give you k is equal to n plus 5. Because if you move this 5 to the left-hand side, you get k in terms of n. K is equal to n plus 5. Now we are almost done. Now you go to the original series given to you and then look at the term given in that series. In this term, now you replace all your k's by n plus 5. Your k is equal to n plus 5, right? So you replace your k by n plus 5. Both of these k's are replaced by n plus 5 to get the desired sequence, desired series. N plus 5 should be in the top. In the bottom, you should have n plus 5 squared plus 3. All I did was I just replaced my k by n plus 5. Pardon. Okay. Now, if you expand this series and this series, you should be able to see that the terms are exactly the same. Okay. All right, that completes that text. If you want, actually, we can, let me actually show you an expanded version of the sequence. To get this sequence, first you plug in n is equal to 0, not sequence, pardon me, series. To find this series, you first plug in n is equal to 0 because the starting index is 0. If you plug in 0, what would you get? It is 5 divided by 5 squared plus 3. And then if you plug in n is equal to 1, you get 6 divided by 6 squared plus 3. And then the next term is 7 divided by 7 squared plus 3, so on and so forth. I'll put dot, dot, dot here, okay? And if you plug in this index, if you compute this series with the starting index k is equal to 5, you should be able to see that you are going to get the same series as this, okay? All right, that completes that example. Let's move on. Okay, next I want to give you the definition of partial sums. What do we mean by a partial sums for a given series? Okay, given a series sigma k goes from 1 to n, infinity, ak, for each positive integer n, we consider the partial sum Sn. Partial sum is denoted by Sn of the first through nth term. That is this nth partial sum. Sometimes this Sn is called the nth partial sum, is defined to be the summation of the first n terms of your series. Okay. If you want, you can write the sigma notation for this one. Your sigma notation would be this time sigma k goes from 1 to not all the way up to infinity. This time only up to n. Ak. This is same thing as this one. You just take the summation up to k, okay? This is what we call the nth partial sum, okay? Since we have defined nth partial sum, now we can define a new sequence in terms of this Sn. That is called the sequence of partial sums. Sequence of partial sums is nothing but Sn, okay? This sequence is what we mean by the sequence of partial sums, okay? So this is nothing but S1, you plug in. Notice that if the starting index is not given here, that is from n is equal to 0 to infinity, okay? Let me put it there. N is equal to 1 to infinity, okay? If you plug in values for n, you get your sequence to be S1, S2, S3, S3, S4, dot, dot, dot. This is what we mean by the sequence of partial sums, where your Sn is defined here. Sn is the summation of the first n terms. Then how do you find the terms of this sequence of partial sums? How do you find S1? S1 is the sum of the first one term, right? First term, that is just A1. That is just going to be A1. What is S2? S2, according to this definition, S2 is the summation of the first two terms of the sequence An. Summation of the first two terms is A1 plus A2. And then what is S3? S3 is the summation of the first three terms, A1 plus A2 plus A3, so on and so forth. Okay, these are the terms of the sequence of partial sums. Okay. All right, let's move on. Let's go over this example now. Find the first 5 terms in the sequence of partial sums for the series, this given series, okay? We need to find the first 5 terms in the sequence of partial sums. Notice that the sequence of partial sums is nothing but Sn is equal to S1, S2, S3, so on and so forth. We are asked to find the first 5 terms of the sequence of partial sums. That means we need to find first 5 terms. Means first term is of course S1, second term is S2, S3, S4, S5. Those are the terms that we need to find. S1, S2, S3, S4, and S5. How do you find this? Well, to find that, I'm going to write the expanded version of this series, okay? So the expanded version of the given series is going to be k goes from 1 to infinity, 1 over factorial k. Notice that we discussed what we mean by the factorial k. This notation means, let me define the factorial k again here. Factorial k is nothing but 1 plus 1 times, 2 times, 3 times, all the way up to k. You take the product of first k positive integers. Okay, so that's what we mean by factorial k. For instance, factorial of 3 is nothing but 1 plus 2 plus 3. That is, of course, 6. Okay. All right. With that definition in mind, let's expand this one. What is the first term of this series? To get the first term, of course, you plug in k is equal to 1, right? That is 1 over 1 factorial. The second term, you plug in k is equal to 2, 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1 over 5 factorial, so on and so forth. This is the series, okay? Now we are asked to find S1, S1, S2, S3, S4, S5. How do you find S1? S1 is just the first term. Remember, partial sum Sn means the summation of the first n terms. S1 means the first term, right? Summation of first term, that is first term. That is, in this case, 1 over factorial 1. What is S2? S2 is the summation of the first two terms. This summation. S2 is going to be 1 over factorial 1 plus 1 over factorial 2. What is S3? S3 is the summation of the first three terms. The summation of these three terms, that is 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial. So on and so forth, you can calculate S4 and S5. Okay, I will leave that as an exercise. And notice that you can simplify these expressions by calculating these factorials. You know how to calculate 2 factorial. 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3. You can compute this one and plug in it here to get the value. Okay. All right. Let's move on. The next thing I want to talk about is the convergence and divergence of a series. Okay. When do we say that a series converges, and when do we say that series diverges? Okay. Here is the definition. Suppose we are given a series, k goes from 1 to infinity ak, is a series whose sequence of partial sums is Sn is equal to k goes from 1 to n ak. This is the definition we had, right? For the sequence of partial sums. Sequence of partial sums means, this is of course the nth partial sum. You take the summation of the first n terms, that is nothing but k goes from 1 to n ak. We say that series converges to a limit L if the sequence of partial sums converges to L. Okay. To check whether, this means to check whether a given series converges, what you do is you analyze the sequence of partial sums. If the sequence of partial sums converges to some L, the series also converges to the same L. Okay. Or in other words, the summation k goes from 1 to infinity, ak is equal to L when this limit is equal to L. Limit of the sequence of partial sum is L. Okay. If the limit of the sequence of partial sum is L, then the summation of this series is also L. That's what it simply tells you. Okay. All right. And also we say that a series diverges if the sequence of partial sums diverges. If this limit does not exist as a nice real number, then we say that the series diverges. Okay. If the sequence of partial sums diverges, then the corresponding series also diverges. All right, let's move on. Let's go over this example now. This is the series that I want to look at in this example. Use a sequence of partial sums to determine whether the series, this given series, converges or diverges. If the series converges, find its value. Okay. How do we determine whether this series converges or diverges? According to the previous definition, to determine whether the series converges or diverges, all what you need to do is you need to analyze the limit of the sequence of partial sums. You need to find the sequence of partial sums, and then you take the limit as n goes to infinity. If that limit exists as a nice number, L, then your series is equal to L. The sum of your series is equal to L. Okay, that's what we are going to do here. Let's try to find a way to somehow figure out the formula for the nth partial sum for this series. Okay. By the way, this series is called the telescopic series. Okay. Telescoping series. So it's a special name. Okay. Now let's try to identify a formula for the partial sum because I want to take the limit of that sequence of partial sums. Okay. What is Sn? By definition, you take the summation from k is equal to 1 all the way up to n. That's what we mean by nth partial sum. 1 over k times k plus 1. Now what I'm going to do is, I'm going to leave my sigma notation as it is. K goes from 1 to n. I'm going to use partial fractions for this expression. Okay. You are familiar with partial fractions from your calculus 2 class as well as in your pre-calculus class. Okay. So this is going to be 1 over k minus 1 over k plus 1. Minus 1 over k plus 1. Now, I'm going to expand this partial sum, okay? Because I can plug in k is equal to 1 to get the first term and then k is equal to 2, so on and so forth. Okay, so the expanded version of this partial sum will be 1 over 1 minus 1 over 2, the first term, plus the second term, I'm plugging k is equal to 2, 1 over 2 minus 1 over 3, third term, 1 over 3 minus 1 over 4, fourth term, 1 over 4 minus 1 over 5, so on and so forth, plus all the way up to the nth term. Nth term is 1 over n minus 1 over n plus 1. Now, as you can observe here, there is a nice cancellation. See, here you have a minus 1/2, here you have a plus 1/2, minus 1/3 plus 1/3. Minus 1/4 plus 1/4, so on and so forth. Finally, this will be cancelled with the previous term. Only remaining terms will be 1 over 1, which is of course 1, and minus 1 over n plus 1. So that's the only remaining piece, right? So let me write it. That's going to be 1 minus 1 over n plus 1. This is the sequence of partial sums. Sequence of partial sums are given by this formula. Okay. All right. Now, how do we determine whether the original series converges or diverges? To determine that, I want to find the limit of this sequence of partial sums. If the limit of the sequence of partial sums converges, your original sequence converges. Okay. Let's see whether this converges. Limit as n goes to infinity, Sn is equal to limit as n goes to infinity, 1 minus 1 over n plus 1. This is equal to 1 minus 1 over, of course, when you take the limit of this expression, this is just 1, right? It's a constant. As limit n goes to infinity, 1 is just 1. And then if you take the limit of the second expression, as n goes to infinity, this n becomes infinity. So it takes the form 1 over infinity. That is 1 minus 0. This form is equal to 0, right? So 1 minus 0 is 1. So sequence of partial sum converges to 1. That means your original series is convergent to 1. Okay, this original series also converges to 1. Or in other words, k goes from 1 to infinity, 1 over k times k plus 1 is equal to 1. That's the conclusion. Okay, your series converges and it converges to 1, and the series converges to 1. Okay. All right, let's move on. Next, I want to go over this theorem. Sums and constant multiples of convergent series. Okay. Here is what the theorem tells you. If sigma k goes from 1 to infinity ak and sigma k goes from 1 to infinity bk are convergent series and c is any real number, then these statements are true. Okay. What this tells you is that sigma k goes from 1 to infinity, c times ak is equal to c times sigma k goes from 1 to infinity ak. What it simply tells you is that if you have a constant inside, you can pull that constant out. Okay. If you have a multiplication a constant multiple inside, you can pull that constant out. Okay. And here is the other rule. This is, if you want, you could call it a distributive, kind of a distributive rule. If you have sigma k goes from 1 to infinity ak plus bk, it is equal to sigma k goes from 1 to infinity ak plus sigma k goes from 1 to infinity bk. What this tells you is that if you have a sigma sign for a summation, you can send this, you can kind of distribute this sigma sign inside the parentheses. You can take the sigma of this one, you can take the summation of this one, and then you can get the summation of this one. Okay, you basically distribute the sigma sign inside the parentheses. All right, let's move on. Next, let me walk you over this theorem. The tail of a series determines the convergence of the series. Okay, to determine the convergence or divergence of a series, all what you need to do is to study the tail of that sequence, tail of that series. Pardon me. Okay, what do you mean by the tail of a series? Well, let's consider this series. First, let me actually formally walk you through this theorem, and then I will come to that. For any integer m, the series sigma k goes from 1 to infinity ak and sigma k goes from m to infinity ak either both converge or both diverge. Okay. In addition, if sigma k goes from m to infinity ak converges to L, then sigma k goes from 1 to infinity ak converges to a1 plus a2 plus a3 all the way up to am minus 1 plus L. What does that tell you? That tells you that, let me first write this, write the expanded version of this series. Okay. By our definition, sigma k goes from 1 to infinity. Ak is nothing but a1 plus a2 plus a3 plus dot 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 am minus 1. M is the positive integer that they are talking about here. Next term is am, obviously, plus am plus 1 plus dot dot dot. This continues forever. You have to take the summation of all the terms in the sequence, right? All right. What does this tell? This tells you that to determine the convergence or divergence of this entire series, it is enough to determine the convergence or divergence of the tail part of the series. If you just determine the convergence or divergence of this part, this is the tail part. You take all the terms up to and including after am, including am. Okay. If this part, if you treat this part as a series, if that converges, your original series should also converge. If this tail part diverges, your original sequence should also diverge. That's what this tells you. Okay. And another thing that this theorem tells you is that if this tail part, this is nothing but, let me actually write the formula for this. This is nothing but k goes from m to infinity, not 1 to infinity. It is m to infinity ak. This is the notation for this summation. Okay. If this part is equal to L, or this tail part is convergent to L, then the summation of the original sequence will be sum of these first m minus 1 terms plus this L. That's what this tells you. Okay. If sigma k goes from 1 to m to infinity ak converges to L, that means this is equal to, this summation is equal to L, then the summation of the original sequence, original series, k goes from 1 to infinity ak is equal to a1 plus a2 plus a3 all the way up to am minus 1 plus L. That is clear from this notation, right? If the sum of all these terms are L, if that summation is L, this summation of the whole series is, you put L here, right? You put L for this whole thing, that becomes this sum, a1 plus a2 plus all the way up to am minus 1 plus L. All right, that is what I wanted to go over. for that theorem. Let's move on. Next, let me recall something that we discussed previously. We discussed geometric sequence. We defined what we mean by a geometric sequence. Geometric sequence was a sequence of this form, right? K goes from 0 to infinity. The sequence of this form is called a geometric sequence. Here, we define something called geometric series. Here is the definition. A series of this form is called a geometric series where R and C not equal to 0 are constants. I'm demanding here C not equal to 0 because if C is equal to 0, everything is 0, right? So the summation will be 0. There is nothing interesting there. So we demand C not to be 0. Okay. So basically what you do is you take your sequence, geometric sequence, and take the summation of the terms of this sequence. This is exactly the summation of the terms of the sequence because you have sigma notation here, right? Sigma k goes from 0 to infinity, C times R to the power k. Okay, or in other words, this is the same thing as the summation of the terms of this geometric sequence. Okay, this is what we mean by a geometric series. All right, next we have this theorem, convergence and divergence of a geometric series. When do we say that a geometric series converges and when do we say that a geometric series diverges? This theorem answers that question. If the absolute value of R is this number involved in the geometric sequence, okay, geometric series. If the absolute value of R is less than 1, then the geometric series, K goes from 0 to infinity, C times R to the power K, converges to the sum C over 1 minus R. If the absolute value of R is less than 1, the geometric series converges. And if the absolute value of R is greater than or equal to 1, then the geometric series diverges. Okay. Okay, let's go over some examples to understand this theorem better. Here is the example that I want to walk you over. Determine whether the following series converge or diverge. Okay, first of all, this is the form of a geometric series. Okay, sigma k goes from 1 to infinity. C times R to the power k means C plus CR squared plus dot dot dot. Okay. All right, what about the first one? Can we determine whether it converges or diverges? To determine that, first of all, I'm going to write this series in this form. Because here, the starting index is 0, right? But in this sequence, the starting index is 5. Okay. Let me write this series first in this form. C plus CR squared. Okay. This R is called the common ratio. Okay. How do we write this in this form? Can we write this given series in the standard form? Well, what I'm going to do is I'm going to expand this. K goes from 5 to infinity. 0.8 to the power K is equal to 0. First, I plug in K is equal to 5 because starting index is 5. The first term will be 0.8 to the power 5. And then plus 0.8 to the power 6 plus 0.8 to the power 7, so on and so forth, right? This is the series. Now, to get this form over here, what I'm going to do is I'm going to rewrite this same sequence. I'm going to rewrite this sequence in a little bit different way. Let's see how we can rewrite it. I'm going to write the first term as it is. Because at the end of the day, this is going to be my C. Because if you compare these two series, pardon me, these two series, the first term is always C. So this has to be my C. So let me leave that as it is. But the next term, I'm going to write that as 0.8 to the power 5 times 0.8 to the power 1. Why is that? Because see, first term is C, the next term is C times R. So I should have the same C in the second term. See, I have the same term times something. That is 0.1 to the power 8 because I need 0.1 to the power 0.8 to the power 6 here. Okay. So next term can be written as plus 0.8 to the power 5 again times 0.8 to the power 2. As you can see, this power is increasing. This is 1, this power is 2. In the next term, that power will be 3. Okay, but this stays the same. It is C. Okay, now you can clearly see that your C, by the way, I'm making a serious mistake here. You need to have plus dot dot dot. Otherwise, we are not getting the right answer, right? Okay, now I can easily identify R and C. C is the first term. All what I do is I compare this one against this one. C is the first term. This is C. And then R. What is your R? Your R is 0.8. As you can see, you have here R to the power 1, and then R to the power 2, and then R to the power 3. See, R to the power 1, R to the power 2, and then in the next term, you will have 0.8 to the power 3. So your C is 0.8 to the power 5. Your R is equal to 0.8. Now you can determine whether this geometric series converges or diverges. For that, you need absolute value of R, right? Since R is a positive number here, your absolute value of R is also positive, that is just 0.8. Notice that it is less than 1. If it is less than 1, by the previous theorem, this series converges to C over 1 minus R. So the given series by theorem 7.26, this series K goes from 5 to infinity, 0.8 to the power K converges to what number? That is C over 1 minus R. Your C is 0.8 to the power 5 divided by 1 minus R is 0.8. Okay, so you can of course simplify this number using a calculator to find the exact answer. Okay, all right, that completes the first part. What about the second one? Second part. Okay, for the second part, I'm going to determine whether, remember, a series converges only if its partial sums, sequence of partial sums converges, right? So I'm going to find the corresponding sequence of partial sums for this series. Okay, if the sequence of partial sums converges, then my series also converges. If the sequence of partial sums diverges, then my series also diverges. Okay, so let me find the sequence of partial sums for this series, part B. Part B, Sn. Sn is equal to sigma k goes from 1 to n ak. Of course, for the second part, your ak is 1, right? This is your ak. So how do I get this summation? If you plug in k is equal to 1, you get a1, right? Your a1 is 1. 1 plus, if you plug in k is equal to 2 here, your a2 is again 1, because this ak doesn't change. The ak is 1 for all k. So you get 1 plus 1 plus. How many ones are there? N ones are there because I take summation from k is equal to 1 to n. So this summation of these n ones will be just n. So I know my Sn. My Sn is n. Now I'm going to find the limit of the sequence of partial sum. If the limit of the sequence of partial sum exists as a real number, then my original series converges. Original series converges. If not, it is not. Okay. All right. So let me find the limit of this sequence of partial sums. Limit as n goes to infinity, Sn is equal to limit as n goes to infinity, n, which is of course infinity. As you can see, it diverges, right? Because this infinity is not a real number. Okay, so the sequence of partial sums diverges. That means our original sequence also diverges. What is the original sequence? K goes from 1 to infinity, 1 diverges. Okay. All right. Let's go over part C now. In the part C, we need to determine whether this series converges or diverges. Okay, for that, I'm going to write the expanded version of this series. This is going to be, if you plug in k is equal to 0 in your AK, this is your AK, of course, you get minus 1 to the power 0, which is 1. The next term will be minus 1. The next term will be plus 1 again, because if you plug in k is equal to 2, if you put k is equal to 2 here, minus 1 to the power 2 is plus 1. And then minus 1, and then plus 1, so on and so forth. Okay, it's kind of a plus 1 and minus 1 are alternating. 1 minus 1, 1 minus 1, 1 minus 1, so on and so forth. Okay, now how do you find the sequence of partial sums? Sequence of partial sums is Sn, that is nothing but S1, S2, S3, dot, dot, dot. This is equal to, what is S1? We have the series here. What is S1? S1 is just the first term, right? Remember, always S1 is just the first term. That is 1. S2 is the sum of the first two terms. This is the first term. This is the second term. If you take the summation, that's 0, right? 1 minus 1, which is 0. What is S3? S3 is the sum of the first three terms. Summation of these three terms is 1. As you can see, this pattern continuous, 0, 1, 0, 1, so on and so forth. What do you think? Does this sequence converge? It does not clearly converge because these are alternating, right? 1 and 0 are alternating. This sequence of partial sums does not converge to a real number L. Okay, these are always 1 and 0 are alternating. They are not converged. Okay, so sequence of partial sum diverges. Sn diverges. What does that tell you? That tells you that the original sequence also diverges. That implies that sequence k is equal to 0, is equal to 0 to infinity, minus 1 to the power k diverges. All right, let's move on. Next, I want to go over this example. Show that each of the sum that follow defines a geometric series, and then determine which series converge and which series diverge. Find the sum of each convergent series. Okay, let's work on the first part. The first part should be very straightforward. First of all, this is the expanded form of a geometric series. A series of this form is called a geometric series, and this is the expanded version of that. C plus CR plus CR squared plus so on and so forth. If you compare this series against this one, you can clearly identify that your C is 7 in this case. This is your C. And your R is equal to 0.9. Okay. So now what can you say about the convergence? Clearly, this is a geometric series because it takes this form. Now we need to determine whether the series converges or diverges. What do you think? Well, look at R. R is 0.9. That means absolute value of R is also 0.9, which is less than 1. Now by theorem 7.26, from this theorem, if absolute value of R is less than 1, this series should converge to this sum, C over 1 minus R. Okay. By theorem 7.26, this given series, K goes from 0 to infinity, 7 times 0.9 to the power K converges to C over 1 minus R, 7 over 1 minus 0.9. R is 0.9 by the way, okay? So that's the summation of the series. This summation is equal to this number, 7 over 1 minus 0.9. All right, that completes that part. Let's move on to the next part. Part B. How do we handle part B? First of all, notice that part B, this series does not have this form, right? This starts at k is equal to 0, or in other words, the summation does not match with what we have here. So you need starting index to be k is equal to 0, or you need this form. Okay, let's try to get this form over here for this for the expanded version of this series. Okay, for that, let me write the expanded version of this series. All right. I changed our example a little bit to make our writings easier. So let's write the expanded version of the sequence series. Pardon me. K goes from 5 to infinity, 1 over 10 times minus 1.1 to the power k. This is equal to 1 over 10 times minus 1.1 to the power 5 plus 1 over 10 times 1 over 10 times okay. We have 1 over 10 times minus 1.1 to the power 6 plus 1 over 10 times minus 1.1 to the power 7 plus dot dot dot. This pattern continues. Okay, so now if you compare this expanded version of the series against this one, your C, you can clearly identify your C to be this number. The C is going to be this particular number. The value of C will be 1 over 10 times minus 1.1 to the power 5. And then can you identify your R? R is the constant multiplicative factor, right? So notice that to get each term, you need to multiply the previous term by negative 1.1, right? If you multiply this term by negative 1.1, you get the next term. If you multiply this term by negative 1.1, you get the next term, so on and so forth. That means R is negative 1.1. That is the constant multiplicative factor that we discussed, right? When we were talking about sequences. All right, we have the value of R and value of C. Now let's determine whether this series converge. This series converges or diverges. Okay, for that I'm going to find absolute value of R. Absolute value of R is plus 1.1. You drop the minus sign, right? Now notice that this is greater than 1. If absolute value of R is greater than 1, then the series diverges by this theorem. Then the geometric series diverges. Okay, so that means the given series diverges. I will shortly write series diverges. Diverges. Given series diverges, of course, by theorem 7.26. All right, let's move on. Next, I want to go over this example. This example is an example where we need to use the knowledge of geometric series to write a repeating decimal as a fraction. Okay, let's work on the first part first. Let me actually read the example. Express the following repeating decimal expansions as geometric series and as the quotient of two integers. Okay, first somehow you need to associate the geometric series for this repeating decimal, and then finally you need to write this repeating decimal as a fraction. Okay, fraction means you need to write that as a number of this form P over Q, where P and Q are some integers. Okay, all right, let's work on this. How do you handle the first part? How do you do the first part? Well, first of all, the first thing that I want you to notice is that if you look at the first part, the repeating unit is 1, 2, 3, right? 1, 2, 3 is repeating everywhere. Let me write the repeating unit here. Your repeating unit is 1, 2, 3. Length of the repeating unit is 3, right? You have because 3 numbers. Length of the repeating unit is 3. So the associated R is going to be 0.001. After the decimal place, you should have 3 numbers, see? Because this length is 3. If the length of this repeating unit is 3, your R is going to be 0.001. In any example, if the length, let's say you have the repeating unit to be 27, 27, 27, then the length of a repeating unit is 2. In that case, your R is going to be 0.01. After the decimal place, you should have 2 numbers, that is 0, 1. Okay, that's how you identify R corresponding to a given repeating decimals. Okay, in this case, we have R is equal to 0.001. All right, next we need to rewrite this number in a different way. 0.123, 123, 123, dot, dot, dot. This is the same as, if you write this in a different way, you can of course write this this way, 0.123. I separate out the first number, this number, and then I'm going to take care of the remaining numbers. Okay, this is going to be equal to, you can check this, plus 0.123 times 0.001 to the power 1, and then plus 0.123 times 0.001 to the power 2, plus 0.123 times 0.001 to the power 3, plus dot, dot, dot. Okay, it's not hard to see that we can rewrite this expression this way. Okay, of course, this is 0.001 to the power 1 means 0.001, and if you multiply that by this, you get 0.000123. That will give you the second set of 1, 2, 3. And this part will give you the third set of 1, 2, 3, so on and so forth. Okay. Now we are almost there. Okay. Now notice that this summation has this form. Has this form given here. Okay. C plus CR plus CR squared. Notice that your C is 0.123. This is CR, C times R. Your R is 0.001 in this case. This is, of course, CR squared. This is your C times R squared. This is C times R to the power 3, so on and so forth. Okay. So your C is going to be 0.123. Your R is going to be 0.001. Okay. Now, notice that absolute value of R is 0.001, that is less than 1. So by theorem 7.26, this series converges. This series converges. Okay. By theorem 7.26, 0.123, 123, 123, dot, dot, dot should be equal to C over 1 minus R, right? The summation of this sequence converges. That means the summation is C over 1 minus R. C, your C value is 0.123 over 1 minus R, 0.001. This is going to be 0.123 divided by 0.999. This is 123 divided by 999. And if you simplify this, you will get 41 over 333. Okay. As you can see now, our given repeating decimal has been written as a fraction. That's what we were asked to do. Okay. First, we wanted to get a geometric series associated to the repeating decimal. Of course, this is the geometric series. And then we use the knowledge of geometric series to find that summation and then write that summation as a fraction. All right, now let's go over the next part B. Again, to handle to do part B, I'm going to do rewrite the given repeating decimal. First of all, notice that in this number, the repeating unit is going to be 3, 5, right? There is no involvement of this 2 in the repeating decimals, okay? Always 3, 5, 3, 5, 3, 5 are repeated, right? So that means the repeating unit is going to be 3, 5. So I always want my decimal place to be right in front of this first repeating unit, okay? So that means I need the decimal place here. So what I'm going to do is I'm going to rewrite this expression 6.2353535 dot 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 as 6.2 plus 1 over 10 times 0.353535 dot dot dot. Would you agree with me? I just separated out this piece 6.2 and then I'm going to add to that this piece 0.0353535. 0.03535 means 1 over 10 times 0.353535. Of course, if you simplify this one, you will get this is nothing but 0.0353535. Okay. Now, if you add this quantity to this one, you exactly get this one. I'm just rewriting this number in a different way. Okay. Now, what I'm going to do is I'm going to deal with only this piece now. This repeating decimal. Okay. Let me deal with that. 0.353535 dot dot dot. As you can see, in that repeating decimal, you have the decimal place right in front of the first repeating unit. Notice that a repeating unit in this case is 35. It has 2 digits. So your R is going to be, your associated R is going to be 0.01. You should have 2 numbers after the decimal place. That should be, the last number should be 1. Before that, you should have zeros. Okay, it is 0.01. Okay, now we know our R. Now let me write this repeating decimal in the desired notation. Dot dot dot. This is going to be equal to 0.35 plus 0.35 times 0.01 to the power 1 plus 0.35 times 0.01 to the power 2, so on and so forth. Just like what we did in the previous problem. 0.01 to the power 3 plus dot dot dot. Don't forget this dot dot dot. Okay, that's very important. All right, now we can clearly identify our R and C. Your C is, in this case, this series has the form of a geometric series, right? The form of a geometric series is C plus CR squared plus, pardon me, C plus CR plus CR squared plus CR cube plus dot dot dot, right? So this series has this form. Clearly, we can identify our C is equal to 0.35 and R is equal to 0.01. Now notice that absolute value of R is equal to 0.01, that is less than 1. That means by theorem 7.26, this series converges. This series converges by theorem 7.26. By theorem 7.26, 0.3535 dot 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 should be equal to C over 1 minus R, right? This converges to C over 1 minus R. That means the summation is equal to C over 1 minus R, which is 0.35 divided by 1 minus R. 1 minus R means 1 minus 0.01. Okay. And if you simplify this, you will get 0.35 divided by 0.99, which is 35 over 9. 35 over 99, pardon. Okay, you multiply both top and bottom by 100 to get 35 over 9. All right, are we done now? We are not done yet because we just found this as a fraction. This repeating decimal is equal to 35 over 9. Now you have to go back and plug in that here because we found this piece as a fraction. So I can plug in this fraction over here. That will give you the desired fraction. Okay, let me add a page here. So my original number. Okay, I'm going to replace this repeating decimal by this fraction. So I'm going to have to put 35 over 99 here. Okay, this will be simplified to 6,173 divided by 990. Okay, as you can see, this is a fraction. That's what we wanted. We wanted to write the given repeating decimal as a fraction. All right, that completes that example. With that, actually, we conclude section 7.3. I will stop there and I'll see you next time.